Okay, guys. So I want to make a review of the construction of the Lebesgue measure. Okay, so all that we have done. Uh, to move this. So I'm gonna do here. So this is the review, and I'm gonna I'm gonna print this as PDF. So I'm gonna load it in course materials, and you can use it in the exam. Okay, so we did several stages to complete the final definition, that is this number 7 of a Lebesgue measure. Of course, this is quite complicated, but the long story short is that basically if if A is measurable or Lebesgue measurable, the outer measure and the inner measure, they're gonna be the same. Okay, so that's probably the more practical way to think about the Lebesgue measure. So you can find it from the outer measure or the inner measure. So it's gonna be a property in the next here. Uh, I'm gonna review also the properties. Uh, if A is number 10, if A is measurable, the outer measure, then the inner measure, and the Lebesgue measure are the same. Okay. So it's basically saying like if the set is measurable, the outer and the inner measure should be the same. So you can, but sometimes you need to prove that it's measurable, right? But if the set is not that complicated, it's not the Cantor set, should be okay, right? So if it sound like look like open, close, something like that, it should be fine. Okay, so well, the first thing we did was define the Lebesgue measure of the empty set equals to 0. Okay. The next step was, okay, that's not giving me too much information. So the Lebesgue measure of an interval AB is B minus A. So over here, you see, I have A and B, the length of this interval. Let's put it in another color. Put here is B minus A. Okay. So next, the next step was, okay, let's get unions of closed intervals, but they don't intersect. Okay, that's when the intersection is empty. Okay, that is joint. So then, so that you have these three closed intervals, right? They don't intersect. The measure of this set of the union of this closed interval is going to be B1 minus A1, B2 minus A2, B3 minus A3. So that's what I put here. Any countable union of closed interval is the sum. Okay, so that's what we have. Now we start becoming astral. So let A be an open set. So an open set can be very weird. I mean, you can uh, just not even graph it. Okay, an open set could be a infinite union of things. So there is no way you can graph it. Okay. So, but so that's why we choose this definition. The Lebesgue measure of an open set is going to be the sum of the Lebesgue measure of the finite union of intervals that are contained in A. Okay. So what does it mean? So let's say A is this open set. So the open interval phi A union the open interval 11, 12. That's my open set. That's A. Okay. So what I'm gonna do is get, for example, let's take first this I1 union I2. So this is this closed interval union the other closed interval. Okay, I1 union I2. So whatever it is, so maybe it's like 5.5 and then 7.5. So you have to take the length the length from here to here plus the length from here to here, and that's the union of that that's the measure of the union of those closed intervals, right? But you have to take the sub. So you see, you can take a better approximation. So you take the red one. So maybe that one is 5.1, and this is 7.9. So 7.9 minus 5.1, and then 11.1 minus 11.9, right? So that will be J1 and J2. So to find the Lebesgue measure, you just make the sum because they're disjoint, so you can make the sum, right? So that's how you had to do the process, right? So and then you see you can do better, right? So you have basically you have to find the sub. So that basically, I mean, it's wrong to think about it, but it's like the maximum. You can think like the maximum length of the closed intervals that you can put inside these guys. Okay. But here we're gonna see that it's basically a minus 5, 3, and 12 minus 11, 1. So there'll be 4. Okay. But the abstract definition is because we're thinking in any kind of set on the real number. Because you see the lecture on Miguel Mascoro, he of Miguel, he proved, he showed that how complicated it is the Cantor set. Okay. Okay. So for the easy sets, even if the definition is weird, it's gonna be okay. It's gonna make sense. Okay. Now, if K is compact, so compact again is closed and bounded. So in the real number, compact is easy, right? So maybe looks very easy, a compact set. But so this definition, this construction is good for any R2, R3. Okay, so it's more interesting if I give you a drawing, a K compact in R2. Although all these steps I just described for the real line. But if K is compact in R2, in the Euclidean space, that's what our book is called, Euclidean space, because the construction is for any not only for the one dimensional, but for R2, R3, and so on. So you have to take the outside, open sets from the outside that contains the K. So for example, G1 is a set, an open set that contains K. But also G2 is a set, an open set that contains K. So what you, of course, what you want to get closer and closer to K, and that's gonna be the measure. So it's basically gonna be the area, right? And so, but that's why you take the inf. So that's, if you want, is again, it's wrong to say it, but it maybe it's easier to think it this way. Think in the minimum of all the open sets, the minimum of the areas of open sets that contain K. And that's gonna be your Lebesgue measure of K. That basically is the area, right? So we know that in R2, this is the area. Okay, so that's how it goes. Then the next step, inspired on these two, measuring A from the inside and measuring a compact set from the outside, we define outer measure and inner measure. So, and then we say that the outer measure is gonna be the inf of the Lebesgue measures of the open sets that contain A. Okay, so that's what we're doing here. So you are taking the inf of the, and then this A is any set. It's not just compact. Okay, that's what I make A. A is the black, so it's kind of closed and open. You see, My A is closed here and open, so it's not open, it's not closed, it's not compact. So this A is nothing in R2, right? Because in R2 it's easier to give an example of what is a compact set or not. And so you see A is not even compact, it's not open. Well, yeah, it's not compact because it's not closed and bounded. Okay. So the inf of lambda, the other measure of A, is gonna be the inf of all those G's that contains A. So that's what he's doing. Okay, just like we explained before. And in the other side, the inner measure is gonna be the suit of the lambda case. So we are measuring A from the inside. But this case, A is any set, not just compact or open as we did before. And now, it looks like we got something good going on here. So outer measure and inner measure, we call this the pre-Lebesgue measurable spaces. We are almost there. So if your outer measure is less than infinity, we say that they are pre-Lebesgue measurable if the outer measure and the inner measure are the same. But the outer measure has to be less than infinity. And then if you remember the presentation of Miguel, of the cantors, of the non-measurable, that maybe, no, Miguel no did Miguel did the cantor set. Or Miguel, somebody did the non-Lebesgue measurable set. So I need to verify who did it. I think it was Miguel. That somebody did the cantor set, I confused. But so for the construction of the non-Lebesgue measurable set, this is how do you construct it. But so it's saying to avoid problems, X is gonna be Lebesgue measurable if for any m that is pre-Lebesgue measurable. So for any m such that the outer measure and the inner measure is the same, when you intersect it with A, that intersection is also pre-Lebesgue measurable. And it has this funny definition, okay? But of course, this is just good for playing with definitions. Okay, so this is our final construction, and that's what I call the Super Bowl. We call it the Super Bowl definition because when I teach this class, usually this definition comes before the Super Bowl. Okay. Okay, so now all this hard work, is gonna give you a really good idea of what is a measure, but this is only for Lebesgue measure. So to define any measure, so there is more than measure. So the probability, a probability is gonna be a measure on a probability space. Okay. So for that, we're gonna have to use the sigma algebras, and that's what you have in the videos. That's what we need to do, sigma algebras to define new measures. Okay, but these new measures hardly are gonna have all these properties that we prove. So many people, a lot of you, I think we prove all these properties. Okay. Number 5, number 6 is homework. Somebody prove approximation property. Somebody prove Kara theory. Somebody prove 10, I think, and so on. Okay. So we did this together. So the Lebesgue measure has all these properties. When we see probability measures or other measures, I mean, you can define a lot of measures, okay? Very abstract way. But, when you talk about stochastic processes, measures are fundamental. So they're gonna explain you how to measure things, okay? So in the stochastic processes, so just to give you an idea why is like real life application, right? Another real life application. So suppose that, so it's a stochastic process. So you have seen, So it has to be doing random motion. Okay. So there is a famous experiment that you have water and you put a pollen particle dust. The particle is gonna start moving like funny and then go down. So she doesn't go, the particle doesn't go straight. So that's called balloon motion. And basically the, the this pollen when it's falling down, the molecules of the water like push it to the right, to the left, and so I start making all this. So that's what in financial mathematics. So you see these famous paths, right? So these are price option investments portfolios. So these are not, these are functions. Yeah, those are random walks. Well, kind of, let's call it random walks, but it's more than that. But those are paths. When you see the investments, those are paths that belongs to Brown and motion, and these functions are not differentiable anywhere. So this function is not differentiable anywhere. So all the calculus that you learn is useless here. But stochastic processes are what people use to do investments. Okay, so that's a great way to make money. Okay, and all mathematicians always wonder why didn't we do study that before to make some money. There is a famous mathematician called Simon's Foundation. I got a grant from his company, and and uh, and but he what he does, he did serious mathematics for a long time, and he did some in Berkeley with the founder of MSRI in Berkeley. He has papers with that famous guy, but then he decided to do investments only, and then he's bigger now, Simons. Okay, so all this to say that behind of measure, this this is probably the people don't talk in mathematics about area. They really talk about measures when you are doing some serious mathematics. Okay, when you want to justify something, you in a lot of fields the concept is measures, and if it's related to statistics, that's how it goes. Okay, probability theory, uh, stochastic processes is very important, and also in Fourier transform and all that. So these measures are going to be very important. So Lebesgue measure is the most important one because it's related to Fourier transform, for example, as I showed you in the first video. That integration and basically the Lebesgue measure gives solutions or just does the serious mathematics behind partial differential equations. Okay, so here the first property says that if A is Lebesgue measurable, then the complement is also Lebesgue measurable. The next one says, number 2 says, you have a countable measurable sets, you made a union, that union is gonna be Lebesgue measurable. And if you make the intersection, that intersection is also gonna be Lebesgue measurable. Okay? Now you have A and B, they are Lebesgue measurable. If you make the difference, they're gonna be Lebesgue measurable. Okay? So that's important for one of your homeworks. But the homework was pretty Lebesgue measurable. But this is important. If A and B are Lebesgue measurable, the difference is gonna be Lebesgue measurable. Now, if you have a countable union of Lebesgue measurable, then this inequality always holds. And this is very useful. And don't get confused because we always think we want to have to prove equality. Sometimes this is enough inequality. Okay. If they are disjoint, you have equality. This, you can think this like a, some people call it triangle inequality. Okay, but you know, but it's just this is very nice. This is very nice. Okay, this is the ideal. Okay, but they have to be disjoint. So that's what this is probably the most important property of Lebesgue measurable. And that's when you with the when of the Lebesgue measure of the Lebesgue measure. This is the most important property of the Lebesgue measure, and that's the one that we are gonna make a definition for any measure. Okay, so any measure must satisfy this one or this one. So we got inspired for this to make any kind of measure. We'll see later the general definition. Now this one is what is homework. It's coming homework, and this is, you have a sequence of sets that are contained between each other. So the Lebesgue measure of the union is the limit of the Lebesgue measure of the set. Now, if A1 is contained in A2, if A1 contains A2, A2 contains A3, and so on, and Lebesgue measure of A1 is less than infinity, this is going to be the limit. Okay, that's an important property. So what are these properties important? For example, use these 4 and 5 to prove the following. How would you prove that the number 5, the measure of the number 5 is 0? You have to prove, you have to use, for example, property 5 or property 6. Okay. How would you prove that the Lebesgue measure of 0 to infinity is infinity? So you'll have to use 5 or 6. I'm not going to tell you because maybe I will ask something like that in the exam. Okay. Or for example, yeah, so those are very useful. Also, this one is very useful. You can ask questions like, yeah, for example, what is the measure of the rational numbers? So you could answer that question with this one. Okay, and maybe with 5 and 6, maybe you can figure it out. But you see, these are questions that in practical sense we will have these answers. Okay. Now, all open sets and all closed sets are measurable. That's why the Lebesgue measurable is the Lebesgue measure is the one that most people use, because you want open and closed set to be the good guys. Okay, because that's how you define continuity. You use open sets to define continuity. If the Lebesgue measure of the other measure of A is equal 0, then A is measurable and the Lebesgue measure of A equals 0. That's kind of weird, but what it's telling you is that because the other measure is easier to find, if you find that the other measure is 0, then the Lebesgue measure is just 0. You don't have to worry too much. Okay. So approximation property, that's what we are gonna use. That's what we are gonna use for the homework 3. It says that A is measurable if for every epsilon there exists a closed set F and an open set G, said that A is between F and G, and the Lebesgue measure of G minus F is less than epsilon. Okay. So those we use that in homework number 3. And property 10, that is probably the relief, is that If A is measurable, the outer measure, the inner measure are the same as the Lebesgue measure. So basically, if the set is a good set, you are okay just calculating the outer measure or the inner measure, and that's a relief. Now, if this is this is not that useful, probably for some kind of problems, but if A is suitable B and B is measurable, then the outer measure of A plus the inner measure of B minus A equals lambda of B. So yeah, so maybe for measurable would be useful for some kind of sets. And then Kara-Theodori is interesting because A is measurable if you just take the outer measure and verify that for any set subset of R, the outer measure of E equals the outer measure of E intersection A plus the outer measure of E intersection A. Okay, and that's it. That's all that we have to. That's all that we have done basically, and then we're ready to move on to sigma algebras. We're going to do sigma algebras, and then define the general measures, and then we're done for the first exam. Or no, more than first exam, midterm, because this is kind of half of the class. It's a middle point. Okay, guys, so I'm gonna make a PDF of this and upload it in course materials.